Our question is, a process has delta H equal to 200 joule per mole and delta S equal to 40 joule per Kelvin per mole. Out of the values given below, choose the minimum temperature above which the process will be spontaneous. Okay, let us see the concept. As we know that delta G equal to delta H minus T delta S. Okay, here delta G is change in Gibbs free energy, delta H is change in enthalpy, T is temperature, delta S is entropy, change in entropy. This process will be spontaneous if delta G equal to negative. Equal to negative. Okay, therefore T delta S is greater than delta H. Okay, so this is the concept. Okay, in the question we have given delta H and delta S, which is delta H is equal to 200 and delta S equal to here 200 joule per mole and delta S equal to, this is per mole. Okay, joule per mole, negative, this is 1. Okay, and delta S equal to 40 joule per Kelvin per mole. Okay, now substitute this value in this equation. Equal to delta H upon delta S. Okay, so T equal to 200 upon 40. On solving this, it is equal to 5 Kelvin. Okay, so the minimum temperature above which the process will be spontaneous is 5 Kelvin. So option 1 is the correct answer of this question.
Hello students, let's start the question. The entropy change associated with the conversion of 1 kilogram of ice at 273 Kelvin to water vapors at 383 Kelvin is. So we have been given a lot of data over here. Specific heat of water and water vapor, that means water liquid and water vapor, is respectively 4.2 kilojoules per Kelvin per kilogram and 2 kilojoules per Kelvin per kilogram respectively. Then heat of liquid fusion and vaporization of water, that is, in fact, this is heat of fusion, liquid, and vaporization of water, and that's been given as 334 kilojoules per kilogram and 2491 kilojoules per kilogram respectively. The log values have been given, yes, so let's proceed. Now, it's very simple to understand this sum. Now, first of all, I hope you know what is entropy. Yes, what is entropy? Entropy is the randomness in the system or the disorder in the system, isn't it? Yes, and gases have the highest entropy. Yeah. So over here, as we can see, the data has been given. The mass of the ice, which can be indicated as small m, has been given as 1 kilogram. Then the temperatures have also been given. The final temperature, which can be written as Tf, has been given as 383 Kelvin, and Ti, that's the initial temperature, has been given as 273 Kelvin. Yes, okay. Now, these are final and initial temperatures, no doubt about it. But then there are going to be a number of transitions which would be taking place, the phase transitions. Yes, so that is very important to be noted of. Yeah. So let us have a look at that first. So now, since all the data has been given over here, we need not write it once again because it would be a very, very long form. Yeah. So let us proceed. So first of all, it's a conversion of ice to water vapor. So it's a very long journey. Look at it. So the very first conversion is from ice, that's from solid, at 273 Kelvin. That's 0 degrees Celsius. It will be first converting to H2O in the liquid phase at 273 Kelvin first. Okay. So that involves what? That involves an entropy. Yeah. Now, first of all, let us write down the conversions. Yes. Now, from liquid 0 degree or 273 Kelvin, it will get converted to water again in the liquid form at its boiling point. That would be 373 Kelvin, 100 degrees Celsius. Yes. Now, from liquid water, it would convert to gaseous water. Yes. At 373 Kelvin, that's 100 degrees Celsius. And then the last conversion would be from H2O gaseous at 373 Kelvin to H2O gaseous at 383 Kelvin. Okay, so that is the final conversion. Yes, no other conversion after that. So now let us label the entropies. This is going to be delta S1. This would be delta S2, this would be delta S3, and this is going to be delta S4. Yes. So now let us have a look. What would be the expressions? Now this one from ice to liquid is that of fusion, isn't it? Yes. Then over here it's going to be liquid to liquid. So that would be the product of MS, that is mass into specific heat capacity of water. Yeah. Then this one is going to be vaporization. Yes. Okay. And again, this would be gaseous to gaseous. So again, there would be your MS involved. Yeah. So let us go on. First of all, delta S1. So that will be indicated as delta H of the transition involved, that is fusion. So here you put your latent heat of fusion value. Yes. Divided by the temperature at which it has occurred. So that would be 334 divided by 273. Yes. And that comes out to be 1.22. Okay. So this is your value number 1. Next conversion involves delta S2. So that would be mass into specific heat capacity into ln T2 by T1. Okay. So that would be T2 by T1 for that particular process. So that's 373 is the final, 273 is the initial in this case. Yes. So mass is 1 kilogram. The specific heat of water has been given to us already, and that's 4.2. Yes. And into ln 373 divided by 273. Yes. So this goes on for the calculation and it gives me the value 1.31. That's value number 2. Yes. Next is delta S3. Delta S3 is vaporization. So over here again, delta H vaporization divided by T. So latent heat of vaporization has already been given to us, and that is 2491. Yes. Okay. So let us put that value over here. That's going to be 2491 divided by 373. There it goes. It gives me a value 6.67. Yes. And then comes in your last one, that's delta S4. Mass into specific heat capacity once again. So 1 into specific heat capacity, and that would be for your vapor. Yes. And that has been given as 2 kilojoules. So that is going to be 1 into 2 into ln 383 divided by 373. This part of it. Yes. So this will be giving me a value 0.05, and that's your fourth value. So what do you have to find out? The total entropy change. So the total entropy change will be the summation of all of these values. So that's going to be 1.22 plus 1.31 plus 6.67 plus 0.05. And that sums up to 9.25. Okay, what's the unit? Kilojoules per Kelvin per kilogram. Yes. So that's 9.25. Okay, we can round it off to 9.26 because this was a number wherein we were having 25 and there were some more numbers. So you can also write it as 9.26. Yes. Okay. So in that case, that matches with our option number 4 over here. Yes. So these are all the calculations involved. I hope you understood the explanation. Thank you. Hello students, let's start the question. Consider the reversible isothermal expansion of an ideal gas in a closed system at two different temperatures, T1 and T2. It has been given that T1 is less than T2. The correct graphical depiction of the dependence of work done, W, on the final volume, V, is. Okay, fine. So basically in this case, as you can see, all of the graphs given over here are flashing mod of W on the y-axis. Okay, so mod of W means whether it's positive or negative, it doesn't make a difference since they have put it into the mod format. So definitely in that case, we are concerned with as to what would be the dependence of this work done on the final volume. So whether it is the work done by the gas on the system or by the system on the gas. Okay, fine. So as stated in the question, it's a reversible isothermal expansion. Yes, okay. Now when it said that it's a reversible isothermal expansion of the ideal gas, the mathematical expression would be W is equal to minus nRT ln V2 by V1. Okay, N is the number of moles, R will be the universal gas constant, and T is the temperature. It's an isothermal plot. Yeah, V2 and V1. V2 is final volume, V1 is initial volume. So let us put it in the mod mode. Yes, so over here we would be putting it up as V final Vf by V initial Vi. Okay, fine. Now final is going to be on your x-axis as stated. Yes, so let us expand this expression. Yeah, so it's going to be W is equal to minus nRT ln Vf minus ln Vi. Yes, okay. What is it? Oh, I'm sorry. Here we had to put out this minus because it has become mod now. Yeah. So now this is going to be nRT ln F minus ln Vi. Yes. Since mod was there, that is the reason we have erased off the minus negative sign over here. Please understand that. Yeah. Now, furthermore, as we expand this, we are going to have nRT ln Vf minus nRT ln initial volume Vi. Yes. So accordingly, if we go to compare it with the straight line equation, it is going to show us that on the y-axis we have W. Yes. On the x-axis we have final volume. The slope is nRT. And see that's the y-intercept is a negative value. Okay, negative of, obviously nRT cannot be negative. Yes, so ln Vi. Yeah, so in that case the plot should actually be in this manner that when you plot your T1 and T2, T1 is less than T2, so it should be going in the downward axis. Okay, so even though if it is over here, then on extrapolation we can observe that it would be touching the value right over there. Yes, on extrapolation we can see it would be over here. Yes, okay. So please remember that on extrapolation we are going to observe the particular values, okay, or the particular intercepts which are being plotted in the options given over there. Yes, so let me just rub this off and draw it again because there was a little bit confusion. So let me draw it once again. Here is your final volume. Yes, here is mode of work, and the temperatures would supposedly, if they are put up over here. Yes, so definitely on extrapolation on the downward direction, you would be able to see that the values would be in negative. Okay, fine. So accordingly, we would be analyzing our plots given. So the first one shows us that it has on extrapolation, T2 value is actually being extrapolated in the negative axis, but T1 is on the positive, which is really not possible. So my first option is not the correct depiction. The second option shows us a slight extrapolation, okay, which is meeting up the 0 value, okay. So that is again not a perfect depiction. In the option number 3 or C, the extrapolation occurs to be, yes, coinciding with the negative axis. T1 is a little, what you could say, nearer to 0, but not totally into 0. So we can say that option number 3 would be the perfect depiction because it is showing us a negative value on the downward axis. Yes, T1 and T2 in your option number 4 is totally not matching with our equation. Yes, so that means option number 3 would be the perfect depiction for our question today. Yes, so on extrapolation you got to check out, even if T1 was a little bit lower on this side, then definitely it would coincide with a more negative value. Okay, this is actually coinciding, but it would be very nearer to 0 in this case. Okay, now since this is not a graph page, so definitely we can't see the value, but yes, it is definitely going to be a little nearer to 0, and hence it is appearing to be 0, but it is not. Yeah, so option number 3 would be a perfect depiction for the plot. I hope you understood the explanation. Yes, on understanding the explanation, you will be able to make the plot. Yeah, thank you very much.